Hey everybody. Today we're doing more volume problems, this time using the shell method. There are times when washers and disks just don't cut it. Here's an example. Find the volume of the solid generated when the region bounded by y equals sine of x squared and the x-axis is rotated about the y-axis. As always, let's start by sketching the region that's going to be generating that solid. There it is. Bear in mind that we're going to be rotating this around the y-axis. So if we want to get washers, we're going to have to draw horizontal rectangles. Unfortunately, the equation y equals sine of x squared does not lend itself to horizontal rectangles. The left curve and the right curve are going to be the same curve. And it's not obvious how we're going to distinguish left from right in this case. So instead of trying to force a round peg into a square hole, let's just draw a vertical rectangle, rotate it around the y-axis, and just kind of deal with what we get. The result when we rotate that vertical rectangle around the y-axis is a thin shell, and the thickness of the shell is going to be the same as the thickness of that rectangle, dx. We want to find the volume of that little shell, dv, in terms of x, and then use the definite integral to add up all those little bits of volume, the volumes of all those infinitesimal cylinders. So how are we going to actually get dv? Here's the idea. Imagine cutting this cylindrical shell open and unwrapping it, laying it out in front of you. The result is going to be a thin rectangular solid. And the height of that rectangular solid is going to be the same as the height of the shell, f of x. The depth of that solid will be dx, the width of that rectangle. And the length of this solid is going to be the circumference of the shell that we started from, so 2 pi times the radius. So now the volume formula for that little rectangular solid is pretty basic. It's length times width times height, so 2 pi r f of x dx. We're really almost there. The only issue now is that we have an r for radius instead of an x. So we need to get the r out and something with x's in. The sketch of the region there on the upper left is the most useful here. The radius is going to be the distance between the axis of revolution, which is the y-axis here, and that vertical rectangle. So just x, the x value that's indexing where that rectangle is. So the volume of that rectangular solid, dv, is going to be 2 pi x f of x dx. For this problem, f of x is sine of x squared, so we get 2 pi x sine of x squared. To get the volume of the entire solid that's going to be generated when we rotate that region about the y-axis, we're going to integrate this over the entire shaded area. So from where the rectangles start to where the rectangles stop. So we need to actually find those limits. We're looking at the sine of x squared. So to find the x-intercepts of that, we're thinking about where is the sine function equal to 0. The first two places where the sine is equal to 0 are at 0 and pi. So we set those equal to x squared. This graph is going to have x-intercepts when x squared is 0 and when x squared is pi. So we get x equals 0 and the square root of pi. So here's our general volume formula. We're going to be integrating the volume of all those little shells over the entire region. So 2 pi integral from a to b x f of x dx. In this case, the limits of integration are 0 and the square root of pi, like we just found out. And f of x is sine of x squared dx. So this is the thing we need to integrate. It's kind of a relief to actually just be doing an integral now and not dealing with all that geometry. In order to do this one, we have to do a u substitution. We're going to set u equals to x squared, the inside function, differentiate, du dx is 2x, solve for dx, and then plug in. When I take out the dx and I put in 1 over 2x du, take out the x squared inside the sign, replace it with u, I'm going to get a cancellation. Those x's are going to cancel. Overall, I'm left with pi times the integral sine of u du. Notice that I wrote explicitly that those limits of integration are x values. After I anti-differentiate, I don't want to make the mistake of plugging those in for u values. So let's actually get this done. We carry out the antiderivative. The antiderivative of sine u that we need is negative cosine of u. Before I plug in, I'm careful to take out the u and replace it with what it's equal to in terms of x. U equals x squared. Now I can plug in the limits of integration, evaluate those trig functions. Overall, I get that the volume of the solid generated there is 2 pi. Let's conclude by having a quick comparison of disks and washers versus shells. So imagine you have a vertical rectangle. There's 2 possibilities depending on how you're going to rotate it. If you rotate it around the x-axis or some other axis that is perpendicular to that rectangle, you're going to get a disk or washer, as shown in that upper picture. And the volume is going to look like pi times the integral from a to b f of x squared dx. That's for a disk. For washers, it'll look like pi integral from a to b f squared minus g squared, where f is the bigger function and g is the smaller function. On the other hand, if you're rotating that vertical rectangle around the y-axis or some other axis parallel to the rectangle, you're going to generate a shell for each rectangle that you rotate. And so your volume formula is going to look like 2 pi integral from a to b f of x dx.